Now that we've set up a fracture for the area of interest that we want to destroy as this creature passes through it, let's start setting up our simulation. And one of the first steps is to set up some decent collision geometry for both the ground and this creature itself. So I've created a destruction geometry object, and let's dive inside here. And I'm going to start by creating a collider for the creature. So we'll drop in an object merge, and I'll point this to object slash creature flying simulated and out squid 3. And in the previous video, I had mentioned that with our bullet solver for rigid body sims, we generally want to give this packed objects as input. That's what Bullet wants to use for its simulation and collision, and this gets a little bit more tricky with deforming objects like this creature here. Now, if you remember from our original setup of this creature, some of these objects are packed objects already that aren't deforming. Like all of these individual ridges along these tentacles, these are not deforming whatsoever. These are all packed geometries that just have a static shape transforming through space. So these packed objects can be used as colliders already without really doing anything else to them to prep them for use as colliders. So I'm going to select all of those based on their path name. So with our primitive selection mode, let's go to our attributes for selection, select by the path attribute, and I'll grab the tentacles ridges, and we can grab these end pieces as well, tentacles ends, and I'll drop in a split SOP for those. I'll call this split tentacles packed. And if you remember from our fracturing setup, all of the fractured pieces of the ground each have a unique name attribute, and I want to do the same thing for these colliders as well. So I'm going to drop in a wrangle here. I'll call this wrangle set names, and we'll create a string name attribute, and I'll set the name equal to collide underscore tentacle underscore. And because we want the names to be unique for each one of these little packed objects, let's add the point number. So do plus, but the point number is an integer, and we need this converted to a string representation of that number, so we can use the I to A function, which will convert an integer to a string. So we'll just pass in the point number. And now if we look at the geometry spreadsheet for these tentacle pieces, look at the point attributes here. Now you can see that each one of these packed objects has a unique collide tentacle name. Now I'm going to start by just using these ridges as colliders without worrying too much about the tubes in between them. I mentioned earlier that in a chaotic destruction shot, you don't necessarily need to have perfect collisions. It looks like some of the gaps in here might be a little bit too large, and this might be somewhat problematic. But for the moment, I'm just going to leave it like this, and then set up a collider for the body. So to isolate the body, I'm just going to drop a null on the second output of the split SOP for the packed tentacles, which gives us the tubes and the main body here. So let's select the tubes as well based on their path attribute and just set those aside. I'm not going to worry about them at the moment. We'll see if we need to create some packed colliders for these tubes, or if we can get away with just colliding with the ridges that we've set up so far. Even though these collisions are going to be imperfect without the tubes inside, it might be good enough. So after splitting aside the tubes here, we now have this main body left over on the second output of this split SOP. And this one is a little bit trickier to create a good collision object for. These are all raw deforming polygons for this main body here, so this needs a different treatment than the packed tentacle objects do here. And we can specify different collider behaviors for our objects. We can set up how these colliders work with the RBD configure SOP, And I should say this is not for colliders specifically. This is also going to allow us to set the various properties for our active simulation objects as well. We're going to use the same SOP to set some properties on the fractured pieces of the ground. But for now, let's connect our tentacle ridge colliders here to this RBD configure. And I'll rename this RBD configure to RBD configure non-deforming. So for these colliders here, we're going to set the active attribute equal to 0. And this will make them static colliders in the sim, so the bullet solver won't try to compute the motion of these things, it'll only use them for collisions. But by default, it's only going to read the position of these objects at the start frame of the sim. If we want this to carry the animation through the simulation for those proper animated collisions, we need to set the animated attribute as well. So let's turn that on in our RBD configure and set that equal to 1. And this will tell the bullet solver to read that animation data as it's running the sim. And really what this RBD configure is doing is it's just a convenient way of setting attributes on the geometry. You can see these parameters we're setting here are just setting point attributes on these packed pieces. We now have active and animated attributes here. It's totally fine if you want to set these attributes in a different way. You could do the same exact thing with an attribute wrangle and just say I at active equals 0 and I at animated equals 1. This effectively does the same thing as what we did with the RBD configure SOP, but it's just a little bit less convenient, and you have to remember the names of the attributes that you want to use when you do it in a wrangle like this. Now there are lots of attributes that you can set on your geometry to control the behavior of these objects, and I would highly recommend checking out the RBD Packed Object help doc. This has a list of lots of point attributes that you can override. You can see the two attributes here at the top that we've just set, active and animated, and there are some more attributes available here that aren't available in the RBD configure. So this RBD configure SOP doesn't represent 100% of the attributes that you can use to control your object's behavior. And if you really want to do some more customized stuff, then you can feel free to explore all of these attributes here. So now that we have these tentacle colliders set up, let's go back to the main body that we were starting to set up here. And as I mentioned, this is deforming geometry, so it requires some special treatment to create some deforming packed objects. And oftentimes, when we're talking about packed geometry, we are often referring to these static shapes that are moving through space, but you can have deforming packed geometry as well. So this body here, as it's twisting and deforming through space, can be packed. So let's take a look at perhaps when it makes this big turn here, like so. We can pack up this deforming geometry. We just drop in a pack SOP here, and then set the display as to bounding box. Then when we're packing deformed geometry, we can still store this inside a packed object, but we don't really get any sort of orientation out of the pieces like we do with the static shapes that are using a transform matrix to move through space. And it looks like there are some strange display glitches happening. So as I have this deforming body packed up here and display that pack, when I'm changing frames, it's actually not changing anything in the viewport here. This feels kind of like a display bug to me. So if I bypass the pack and turn it back on, you can see now that position is changing. Let's try turning the display as back to full geometry. And you can see that even though this geometry is still deforming and being packed into a packed object, it's behaving slightly differently than our other more standard packed objects. Maybe if I drop in a packed edit and set this to bounding box display and template view that, we can get a better look at what's actually happening here. Yeah, there seems to be something kind of strange going on with this bounding box display updating here. But in any case, we can still pack this deforming geometry and create a convex hull for this collider on every frame. Now, if we were to perhaps do a shrink wrap to create a convex hull and connect that to our deforming input, this would give us a convex hull that we can use for collisions, but it's possible that this will have changing topology on every single frame. So if we take a look at this is currently 1,743 points. Let's jump ahead to another frame. Now it's 1,706 points, and we always want to have some consistent topology for our RBD colliders. And maybe it would work okay with this changing topology, but I don't really trust it. So what I'm going to do is create this shrink wrap at a static frame, and then I'm going to point deform that shrink wrap or cloth deform it to follow along with the animation. So there are a couple ways that we can do this on a rest frame. Let's delete the pack and the packed edit. One option would be to just pick some frame of our animation to use as our rest. So I could do a time shift, maybe time shift this back to frame 30, drop in that time shift just before the shrink wrap, so that will do the shrink wrapping at this one reference frame here. And then we can either do a point deform or cloth deform, which are almost the same thing, to get this to follow along with the animation without changing its topology at all. So if we want to do this with the cloth deform, we would have to do a cloth capture first. So we'll plug the shrink wrap into the first input of that, and then do the capture based on the original render mesh, which is this time shifted version here. Plug that into the second input. And then we can apply the deformations by passing this into a cloth deform. So for the cloth deform, the rest cloth is the time shift. The geometry to deform is the output of our cloth capture. And then the deforming cloth is going to be our original animated main body here. So now we have this shrink wrap geometry being deformed to match the animation of this creature, and it's always going to be constant topology because it's just been generated at a rest frame, and this makes for a nice collision mesh. Now, it's totally fine to do this time shift thing, but sometimes it's preferable to build your collision meshes at a rest position instead of just at a time shifted frame. And it's good practice when you're creating assets to bake in some rest position data. It looks like for this creature here, we haven't actually baked in any rest position data here. But in our case, we do have the original model available to us at its rest pose, so we can try building it based on that instead. So I'll just do an object merge, point this to object/creature/out-creature. And to isolate just the main body, I'm going to use the tentacle attribute. So let's do selection based on this tentacle attribute here. Select the tentacles themselves, which have a value of 1, and hit delete. And it looks like our tentacle attribute is a float. That probably should have been an integer, but it's kind of interesting that when we deleted based on a decimal value, Houdini has actually given us a range in our blast here from 0.5 to 1.5 so that we don't run into weird problems blasting based on a float value, where we might want to include some values that slightly deviate from the value that we've selected. So now that we have this main body in its rest position, we can shrink wrap this instead, but we do have to watch out for some of the different scaling that we've done at different points in our scene. So let's pin our viewport here for the moment and go back to our creature flying tentacles. And diving back inside that creature flying simulated here, you can see that we have this creature scale of 0.7 being applied at that point. So whenever you're doing a point deform or cloth deform between things that are in different scales, you have to kind of watch out for that sometimes. So to be safe, I'm going to copy this creature scale and then go back to our destruction. And just to be safe, so that we don't run into weird deformation issues when we do the cloth deform, I'm going to paste in this creature scale after we've isolated the body in its rest pose here. And if we display that, that scales it down to the same size as the animated creature. This creature scale transform that we copied also flips it 180 degrees. It doesn't really matter whether we do that or not in this case, but I'll just erase that so that we're just getting this uniform scale of 0.7. So now that we have this rest position with that creature and the correct scale, I'll do the shrink wrap based on that. We can delete our time shift because we're not just doing a frozen frame for our rest position anymore. And for the cloth capture reference, that's just going to connect to our out creature after the scaling as well. And then for the cloth deform, we're going to connect the rest cloth to our creature scale transform and the cloth deform to the animated body. So either technique will work fine. I generally do prefer to do things in the rest position when I have rest positions available, but it's good to know both options. So just checking our final output of this shrink-wrapped collider. It does look like we have a few unconnected points, as you've seen a couple times in the past. Anytime we have these stray points, I like to clean those up. I'll turn off remove degenerate primitives, leave on remove unused points, and I'll drop that right after the shrink wrap. So that gives us some slightly cleaner geometry. And I also want to name this mesh as well. Over on the tentacles, we set these names to collide tentacle with the point number. I'm just going to copy this set name wrangle here, and I'll paste it after the clean following the shrink wrap. And for this one, because it's just one mesh, we don't really need to set multiple names based on the point number. I'll just set this name for this mesh to collide underscore main body and delete out the point number there. So even when we only have one object as a collider here, we still want a valid name on this, which we're going to pick up when we assemble it. And let's also create some normals on this deforming geometry. Just good practice and can make things display a bit more nicely in the viewport. And then do that assemble. As before, we're going to turn off create name attribute because we have a good name already. Turn on create packed geometry. And now that we have a nice packed object for this body here, we can go ahead and do another RBD configure on this. And this RBD configure is going to be pretty similar to the one that we set up for the tentacle ridges. We're going to set the active attribute equal to 0. But in this case, we don't need to set the animated attribute because we don't need to just read normal animation data for the transforms moving through space. In this case, we want to set the deforming attribute. We'll turn on deforming, set that equal to 1, and that will tell the bullet solver to recalculate the collision shape for this object on every single frame. And now I'm actually noticing a bit of an issue with how we've set the name attribute on our geometry. So we've set this with an attribute wrangle that's running over the points, which means name is a point attribute, and this won't get correctly picked up by our assemble sub. If you look at the geometry spreadsheet for that assemble, you can see the name is just creating a new name for this piece. So let's keep this always on top. And then on our attribute wrangle that's setting the name, let's tell this to run over primitives instead, which means it'll create a primitive attribute. And now that name is a primitive attribute, now it's correctly picked up by the assemble SOP and passed on to the points of the packed objects. And setting the name attribute correctly on prims or points is a fairly confusing thing when you're new to destruction work. So basically, any time you're working with a name attribute, it should be on the primitives for the raw geometry like this, and it should be on the points whenever it's packed geometry that's going into the sim like this is. And this is why when we set the names on these pieces of the tentacle that we're colliding with over here. In this case, these are already packed objects, so these can have their name on the points. One way that I like to think about this is when you do a rigid body sim, all of the rigid bodies are almost like fancy particles that have a more complex collision shape. So when we're talking about what's essentially a fancy particle sim, even though that's a bit of an oversimplification, we're talking about particles points. All of the important data on rigid body packed objects should be on points. As I mentioned before, we can set a primitive name attribute as well for ease of selection in the viewport and that sort of thing. But I usually give that a different name, like name prim, since that's a special case and it's not really used as part of the simulation info. Okay, so we have point names on all of the packed pieces for the tentacles. We have that name primitive attribute on the raw geometry for the body, and then that's getting assembled properly into a packed collider object. This RBD configure is for our deforming collider. And now we can merge these together. So I'll just drop in a merge sub, connect the tentacle packed pieces, the deforming body packed piece, and display those together. And this should be good enough for our rigid body collisions in the simulation. As I mentioned earlier, the gaps in these tentacle ridges might be a bit problematic. For my original simulation for this shot, I just collided with the tentacle ridges like this. But just to be extra safe, let's make some collider shapes for these tubes as well.